we kick off. So welcome everybody. This is the Impossible Metals monthly webinar and podcast for the month of August 2025. I'm super excited to have Shane join us from ReElement, and he's going to give a really interesting talk on unlocking deep sea minerals with flexible refining solutions. So over to you, Shane.
Hey everyone, thank you for joining this morning. I see some familiar faces in the crowd here, so really excited to have you. Start out, my name's Shane Tragethon. I lead business development and partnerships for ReElement Technologies. Nuclear Navy, as well as primarily working for the U.S. Department of State overseas, spending a lot of time in Africa. So really excited to share a little on our technology today. Kind of how I'd like to do this is talk a little and go through ReElement and what we do, and then discuss kind of how we partner with Impossible Metals, what we can do. And I want to give you guys plenty of time for a question and answer session today as well. So I'm going to jump into the presentation, and looking forward to sharing. Can you guys see the presentation all right?
Yes.
Excellent. We are ReElement Technologies, and what we do is the refining and separation, and I think we do it better than anyone else in the world, for a variety of reasons I'll tell you about today. We can go from anything from recycled materials, from concentrated ores, from deep sea nodules, as well as concentrated brines, and bring elements up to high purity. So normally, let's say we're talking battery grade rare earths, we go to 99.5. For lithium carbonate for batteries and nickel sulfate and cobalt sulfate, 99.39 is really good. When you're talking about some of the other strategic metals, and this could be stuff going into optics, it could be stuff for materials for preventing airplane turbines from getting too hot, we can go up to 5 nines for that, as is required. Just a quick forward-looking statement. We do, one of our owners is American Resources. They own 20%, or I should say 19% of our company. And so there are some forward-looking statements in here. But everything I say today will be pretty much in the open, just bringing everything together. We focus on rare earth elements, critical minerals, and defense metals. This is everything from rare earth elements for magnets, and this is like neodymium and praseodymium, as well as terbium and dysprosium. The light rare earths, like neodymium and praseodymium, make magnets really strong, and that's how you get a strong magnet. And the heavy rare earths, like dysprosium and terbium, prevent magnets from demagnetizing with heat. We are refining the heavies today in the US, which is really unique. The other company doing this outside of China is Linus, and we're producing the heavies every day at our facility in Indiana. We also refine lithium. We go to lithium carbonate. We do this from brines, from recycled materials, as well as from ores, and cobalt and nickel. We can go to the nickel sulfate and cobalt sulfate, as well as if going to the hydroxide is required, we can do that too. What makes things interesting, and I'll get into this later, is the output of our process. So cobalt sulfate or nickel sulfate can go directly into an electrolyzing process to go to the metal. And that can get really interesting for one, logistics, and two, for needs, especially when you're dealing with high purity. We have a complete solution to rare earth elements and battery elements and defense metals. So we can take in the black mass from batteries and then output something high purity that goes into new cathode active material for batteries. And it's the same from ores. And we'll get into nodules later, but they have copper, they have nickel, they have cobalt, and they have manganese. One of our pride and joys is the fact that we are economically competitive against China. When the lithium market was down around $10, $11, you started seeing Chinese demand or Chinese processing plants start to close down around that. And that's with support from, they have support from the Chinese government. With us, we still had some margin in there. So we can compete on price, and we get excited about this. Our technology is modular, scalable, and versatile. So our technology is based on columns with resin in it. I'm going to show you about this, but we can build to whatever the demand is and whatever our supply is. We're not based on building a nameplate capacity facility like you would see in China and other industries for processing. And as I mentioned, we're multi-material, multi-feedstock, and we can go to high purity. For us, we focus on kind of the Rockefeller model with Standard Oil. We want to build processing facilities, and it's not a single facility. One of the benefits of our technology is we can develop these across the US and around the world. So we're not, since they have lower CapEx, capital expenses for building these facilities, we can deploy them. And what that really does, and if you look at, let's say, the EV supply chain for lithium today, and same with rare earth elements. A lot of these elements are mined around the world, could be Australia, could be Africa, could be in South America, and then they're shipped to China for processing, and then they're shipped again. And every time you ship these, it's increasing the carbon footprint, it's increasing cost, and it's just making things less economic. If we can move refining closer to the source and compress the supply chain and do that value addition closer to the source, it reduces reliance on a single refiner, but it also lowers cost. And so if we can stay competitive on costs in the US, then moving our refining facilities closer to the source, we can really provide a lower cost for the rest of the supply chain, and that's critical. As I said, we're cost competitive and high purity. We're modular and co-locatable. So if we're looking at battery recycling, we can put our processing plant at the battery production facility. If we're looking at modules, we can put them at the closest port. And I'm sure at some point in the future, there may be a possibility to put them on a ship. And again, lowering logistics. That's still a ways out, but as we're looking at this, we really want to compress the supply chain. Byproducts, we minimize waste. Legacy technology, and I'll get into this in a bit, is solvent extraction that does a similar process. And you see this in China. And one of the, I don't want to say attributes, but acid waste comes out of solvent extraction by design. It's adjusting pH, and so you have a lot of acid waste. One of our main byproducts is salt, and that's because we only use the exact amount of reagent as is required for the separation. And we can recycle that salt through various techniques, bipolar electrodialysis or chloralkali process, to recapture a lot of those acids back into our process, and then also recycle a lot of the water coming out of our process back through there. Environmentally superior, as I mentioned, we don't use toxic organic solvents. We don't use any organic solvents in our technology, and that makes a huge difference environmentally, as well as lowering the acid requirement as well. So it's a generational, it's a disrupting technology for separating materials. And then because we can deploy globally on this, there isn't that single choke point, which we are facing today. We are heavily tied into the U.S. Government with the defense, energy storage, and then commercial vehicles, and then supporting the aviation market. As all these industries are growing, we can help support their growth, as one of the real choke points today is refining. And we've seen this even as soon as earlier this year, as recent as earlier this year, on the inability for different companies to get the materials they need to produce these products for the electrification and as well as national defense. If we look at supply chains and where things come in today, the heavy rare earth elements, they come from China. The light rare earth elements, 87% come from China. Antimony, gallium, germanium, lithium, cobalt, nickel. Gadolinium, another rare earth element, is primarily processed in China. There's very few refining places outside of China. And even China doesn't have a lot of the mines on this. What they're doing is they're importing this product and refining this. So for us, it's just an opportunity to decentralize and scale around the world the refining capacity. Tariffs, it really helps us, or I don't want to say it doesn't help us as much, and it doesn't hurt us. As we can do this processing in the US, it allows the material to be imported, and we can process it locally. So some of the tariffs that we're seeing are on these materials that's raising the prices. And so we can help the US with their supply chain. For national security, rare earth elements are on a variety of fighter jets and nuclear submarines, drones, satellites. They're all required. If we look at magnets, a friend basically described computer chips as the brain. So whether it's going to be AI or any of advanced technology, the chips are required for kind of getting the computer to process. The batteries provide energy. That's like the circulatory system. And magnets are the muscular skeletal system of technology. So they convert this energy into motion, into physical motion. And that's why they're so important. You see them everywhere. It's from your iPhone to your EV, to the fans and the hard drives in the data centers, which are driving AI. So it's all over. And with these other elements, it's the same. You see the same, where there's a thread that links them throughout technology and the growth. And it comes back down to the elements in there. Digging into our technology a little more, the current technology is solvent extraction. Use hundreds or thousands of mixers and settlers that produce a lot of toxic waste, and they get discharged into lakes in China. And it's horrible for the environment. Just because it's done in China doesn't make it any better for the environment. There's a better way to do this. For us, we use chromatographic separation. It's We use columns with resin in it. Our resin is really small. If you look at it under a microscope, it looks like a golf ball with holes in it. So you just have this huge amount of surface area. And what we've done is converted a liquid-liquid process to a liquid-solid separation process. And with this, it allows us to use less reagents than traditional solvent extraction, which lowers operational costs. And we don't need those organic solvents that I mentioned, where our hazardous waste is extremely low. And the surface area on our resin is orders of magnitude bigger than what you get in solvent extraction. With solvent extraction, it's kind of like a washing machine where it creates a bunch of small bubbles, and then all the interactions happen on the surface of those bubbles. And the organic solvent kind of works like the detergent to kind of froth everything up. With us, we just drive our solution through our columns. As I mentioned, we don't use aqueous chemistry as much. It goes to a liquid solvent interaction, so we're not trying to drive those liquid surface interactions. Our footprint is so much smaller. Instead of acres and acres of mixers and settlers, we can do it in a small area. We're talking 25 or 30,000 square feet can replace acres of mixers and settlers. And then we also, the technology, especially for rare earth elements, has been around since the Manhattan Project, whereas a side project to separate some of these rare earth elements. For them to do it, though, it would take a couple weeks of experiments. You're trying to go through 20 different variables. It costs a couple $100,000 each time. We now have a predictive simulation, a digital twin that simulates what's going through our columns. And so what used to take weeks, we now can do within just a couple hours. I want to highlight the key parts of our technology. It's a new refining technology. Since we have less CapEx, we can scale up. We can go to high purity. We can deploy and scale globally. It's sustainable, especially when compared to legacy methods. And then we can co-locate. And then we also can keep that quality control, where what we've seen in magnets coming out of China is a variety of elements that are mixed in. They're not that consistent in what's inside them. And same with batteries. When you look at lithium batteries and runaway fires, impurities is one of the reasons for this. And so if you can lower those impurities that cause those basically spikes in the lithium batteries, you can actually make the batteries safer as well. Highlighting a lot of the feedstocks here, can be natural minerals, it can be spodumene, it can be stibnite for antimony, it can be different ores for rare earths. We can do recycled magnets, we can do tailings, and manufacturing scrap, and then also deep sea nodules. As I mentioned, our goal is to decentralize and not just do this in the US, but really help expand to Europe and partners around the world. We have a partnership with Novare in Africa to put in a refining facility in South Africa. It's really exciting because, again, that's driving this closer to where most of the minerals are coming from. One of my favorite graphics, and one thing you have to consider is just scale. Yes, this is a big facility that's been going on for years, but even though those are pretty colors, they aren't good for the environment, and they have heavy metals in those lakes. With us in Indiana, we're next to a church, a fencing club, and a kids ninja gym, and we're permitted in under 2 months. We don't have hazardous output. Just an initial list of purity of some of the elements that we are able to purify. And this list is growing by the day as we get a new customer request. As I mentioned, the nickel, the cobalt, the manganese are all on this list. We're working on copper as we speak, and those are all in deep sea nodules. A few pictures of our Noblesville facility. This is our commercialization facility. It's been growing. We didn't intend it to be a production facility, but we're now doing small scale commercial production there. And then Marion, this is the old RCA Thompson facility. They used to be the largest tube TV manufacturer in the world. And now when flat panel TVs came about and production moved to China, Korea, and Japan, Marion went out of business basically. And so we have taken that over from the city, and we're developing that, and that's going to be our full-scale industrial facility. Originally, this technology came out of the coal industry, or at least that's how our co-founders found the technology. They're doing a lot of remediation and owned metallurgical coal mines and processing plants for steel. But when you have this, you have acid mine drainage, you have tailings, and you want to remove those metals. And the old way was just to dump chemicals into the water. So they started looking for new technology where they could separate and purify these elements and help improve the environment and still provide an offset, an economic way to do this. They went university to university, and they ended up at Purdue University meeting Linda Wang, who in partnership with Eli Lilly developed this technology for the production of insulin. So before this technology, insulin was produced using pig tissue. The technology has now been developed to be used in its use today, producing fructose and separating glucose and fructose. It's used in the petrochemical industry for separating different benzene compounds. And then we are applying this to rare earth elements and critical minerals and defense metals. We're working with antimony and bringing it in and purifying it. And then I want to highlight some of our industry partners. You may have seen news earlier this week about a great partnership we have with Vulcan Elements. They're a fully U.S. Magnet manufacturer with no Chinese equipment, and we're helping provide their support their supply chain. POSCO International is an amazing partner. Milwaukee Tools, Siemens, and Pensana, a rare earth mine in South Africa, and I already mentioned Novare. And we work closely with the Department of Defense and Department of Commerce, USTDA, and EXIM. I'm a veteran. We have a lot of veterans on our team and former workers of the U.S. government. And so we're very, very well tied in. And I just want to highlight our team on here. Some of the key points, aside from Mark Jensen, our chairman and CEO and co-founders. Jeff Peterson, he was in the nuclear Navy. Bob Gallion, he helped build CATL, the largest battery manufacturer in the world, from zero to $180 billion. He was their first CTO, and he developed it with Robin Zhang. Yi Ding helped develop this technology in partnership with Linda Wang on here. He's on a lot of the patents. Kevin Higgins was the former chief of staff at the CIA and did a lot of work in Africa. Mark Gilbert, former U.S. ambassador to New Zealand and Samoa. That's who we are. And love to answer some questions.
Well, thanks a lot, Shane. That was really interesting and a big. So maybe I can kick off so if people want to use the raise hand icon in the bottom of the screen, that will just in the order you raise your hand, and then you can unmute yourself and ask a question. My question would be, what do you think makes polymetallic nodules a good fit for your technology?
I think one of the biggest things is we're a multi-feedstock solution. And so with polymetallic nodules, in order to get to high purity elements for all of these, you're going to have to go through a few different mills smelting to capture the manganese and the cobalt and the copper and the nickel, as well as any of those other elements in there. Some nodules are very high in rare earths. So traditionally, you would basically have to refine the material, and then there'd be slag and that waste, and then that slag would have to go through another step and be refined, and then it would have to go through another step. And so you've got to go through a few different refiners to finally get to that product, and then you're still going to have waste. That increases the cost so much. With us, getting the nodules into solution, we can then purify all those streams all at once. So anytime you are lowering those steps to those refining process, it lowers the cost, and then you can get individual products at a lower cost for the rest of the supply chain. So one of the most interesting things about the polymetallic nodules is the fact that they're polymetallic, and that's what pairs best with our technology.
Yeah, and to follow up, so what about how to kind of get them into solution? Because from my understanding, your approach is once they're in solution, you can then pull out each of the metals. But what are your recommendations for that first step?
So with any hydrometallurgical process, that's the very first step, is getting it into solution. So that would be usually for nickel and cobalt and copper and manganese. We've worked with all these, and it is through an acid. We use a weak acid in our process, and I don't want to go too deep into kind of our processing, but traditionally through chemistry, you dissolve them and leach them with an acid, and then it would go through our process. And so there are various processing steps, but that's kind of the basis for getting them in.
Yeah, and would you take care of that, or would you work with a third party?
We would have to determine as this scales up on what the best fit. Where our technology really fits is in that separation step. Now, that's the change. There are hundreds of years of metallurgy of getting materials into solution, and there are companies that are fully capable of doing this, as well as engineering firms who can design processes specifically for this. So at our scale today, and the amount of nodules that are coming off, we can get it into solution. When we're looking at a full production plan, I think whatever the lowest cost solution to produce that final product is what we'd likely go with.
Yeah, and I'll just mention, as I think some people know, we spun out a company called Viridian Biometals that is really focused on just that step of getting metals into solution, but using bacteria, but not leaching. So it's a potential synergy, but they're an independent company. So we do have a question. First question, Eduardo. Do you want to unmute yourself and ask your question?
Hi, everyone. Thank you for the presentation. I wanted to ask you if you are, because you said your solution is modular and stackable, if you're planning to be near ports with mobile modules, or if everything will have to go to process to your things in Indiana you mentioned. And also I wanted to ask you if you foresee any problems with the fact that the modules come from the sea instead of coming from the standard process where you get your livestock stock now. And lastly, what purity are you targeting for these nodules? Thank you very much.
One quick thing, and Eduardo, would it be all right if you introduce yourself? I'd love to hear where anyone asking questions, who they are and their background.
Apologies, I should have done it. Thank you very much for giving me the opportunity. My name is Eduardo Zarghetta. I'm an investor. I'm new to this specific sector. I invest in defense, energy, and AI infrastructure. And I think your company, Impossible Metals, sits right at the intersection of these sectors.
Thank you, Eduardo. To go through your questions one by one, as I mentioned, our technology is deployable. And we want to bring this technology as close as possible to wherever the source is. So in the case with Impossible Metals, it would make the most sense to deploy wherever the nearest port is, because if you are moving material from the ocean to a port, shipping it by train or truck to get to somewhere else, every step you do is going to increase cost. So I'll give you an interesting example of how much of a difference this makes, and it's going to be very similar kind of across. It's just what the concentration is of the element. So for lithium coming out of the ground is anywhere from 0.5% to 2%. It's beneficiated, and they go through a concentration step, and it goes up to 5.5% to 6% for spodumene. It's then shipped all the way around the world to China, and then it's produced. Now, if you can move that material, and we've seen material coming out of the ground at 1 or 2% and just being shipped like that. So if you are moving, let's say 2% to 6%, that's 30% of the mass that you are moving. So that's 1 truckload instead of 3 truckloads. Now going from 5.5% or 6% to battery grade lithium carbonate, that's about 1 truckload to 7 truckloads. So you're basically going with, let's say, around 21 less truckloads by doing steps closer to the source and processing next to the source than you would just doing traditional shipping. You're going to see similar logistics questions with these rare earth nodules. Is how can you beneficiate and upgrade the material and refine the material as close as possible to the source, and that just drives a lower cost, and it's also better for the environment. The next question, forgive me, Eduardo, I forgot your second question.
If you see any problem with the nodules coming from a sea environment.
Yeah, absolutely. We do not see any modules coming or any issues with the nodules coming from the sea. As I mentioned, our process starts when it's already in solution. And so once it's going into our columns don't ask, oh, where'd this come from? Was this from a battery? Was this from the ocean? We just look at the composition of what the material is, and then our process is driven based on the composition of the material instead of its source, if that makes sense.
So, Trevor, I think you're next. Please unmute and ask your question.
Yes, Oliver, thank you. Dan, good to see you. I'm not sure if we met when I was out in the Indiana office, but chatted with Kurt and some of the guys in the Africa team as well. I know you guys ran a meeting yesterday about Africa. Could you give some sort of like forward-looking statements around like what we have to look forward to what y'all are doing in Africa.
Thanks, Trevor. You definitely know a lot. I don't think we met. I'd say a few different things to highlight. One is our partnership with Novare. They've committed to building a $100 million facility. It's likely going to be in South Africa to start. And again, that's going to be a mixed feedstock facility. And I keep hitting on this mixed feedstock and polymetallic because it really drives the flexibility of our technology. And so that's the first and foremost project. You'll also notice recently we've signed an agreement with Pensana. One, that's an offtake agreement. Pensana is in Angola, a country that the U.S. has a great relationship with. And it's a way to get these rare earth elements into the U.S. The other part of that is more moving into a greater partnership, and that could mean deploying our technology to Angola, or it could be a variety of different partnerships agreements. But those are the two big ones that we'll focus on.
That's exciting. Yeah, I'm going to be chatting with Ben and Kirk probably next week about some other opportunities for y'all in Africa. And then just one follow-up question with your relationship with Impossible Metals. I know that's newly established. What geographies are y'all targeting for the seabed mining, like up front? And then, are there any geographies that you're trying to get into that you haven't been able to get?
Yeah, I think for the Impossible Metals and their geographies, I would like them to kind of speak to that. We're not the miners here; we're just the refiners. And then I think we can go with that.
Yeah, I can answer that. So our strategy is to form partnerships with people that have resource areas. Many of them have had for over 2 decades. And so we bring technology and help commercialize an area that is basically ready to submit a commercial license. So those are likely to be in the Clarendon-Clipperton zone. We have a number of partnerships that we have signed with resource holders in the Clarendon-Clipperton zone, which is the area between Hawaii and Mexico. We also have a relationship in the Cook Islands. And you may also be aware that we have kicked off a leasing process with the Department of the Interior around American Samoa. I would see that order. The American Samoa is a brand new application, so it's going to take some time. There has to be a bidding process. We have to win the bid. We have to do the exploration work. So that's probably the longest out. But the Clarendon-Clipperton zone, there are some contractors there that have had areas since early 2000s, so over 20 years, and so are quite ready to go to production.
Okay, that's exciting. There's also some deposits off the shore of Japan that is like a current bidding process open for that we have some access to. So we might want to talk about that at some point.
Yeah, we've had some discussions, and we're quite active in Japan. So yeah, Trevor, let's reach out and we can talk a little bit. But let's keep going. I notice George. Yeah, thank you, Trevor. George, I think you're next on the list.
Okay, great. Yeah, thanks for the talk. Very exciting. George from Capgemini Ventures. I work for the Ventures unit of the consulting group. I'm based in Europe, so I would first be interested in your European perspective. And then I also have a question that's more that you already talked about in terms of supply chain design, whether it makes more sense to bring the refining to the source or to the market, or is it a hybrid case by case approach that is needed? That could work best to design that.
Yeah, thank you, George. Those are both really good questions. Since we're a small and growing company, as just like Impossible Metals, our model is partnerships as well. So we are developing partnerships in Europe. We have some in place. We're always growing those. So how can we help supply the European market with the materials that they need is one of the questions that we deal with, and how can we solve that problem? That could be anything from recycling wind turbines to importing elements from around the world into Europe for refining. It's going to kind of jump into that second in supply chain design. With any supply chain, compressing kind of the front end lowers the cost, and the reason is you're just moving less material. So for that, when there is the opportunity to deploy near the source, that's something we definitely want to look at. Does that mean that we're not going to import material into the US or Europe? No, that doesn't mean that at all. In fact, we're going to be doing that as well. So I think the answer to your question is it's always going to be on a case-by-case basis, and you're going to be looking at costs and what makes more sense. But I think in the end, as an overall high-level strategy, it's going to be a hybrid approach. Are you going to be processing near the source? Yes. Are you going to be importing somewhere else? Yes. The overall goal is to kind of grow the supply chain, and that lowers costs and makes things economic for everyone involved. Does that answer your question, George?
Yes, it does. Thank you. Do you already have a presence in Europe, or what's your status on that?
We have some partners we're working with, but we do not have a ReElement Europe like we do a ReElement Africa right now.
Okay, thanks.
Tony, you're next.
Thank you, Tony with Deep Sea Vision. Oliver, you and I have crossed paths a couple times. Thanks. Good presentation today. A couple questions on we do AUV. We have a Hugin, some deep sea sonar equipment. We do surveys pre and post for mineral surveys. We did some work in American Samoa and the Cook Islands this year as well. We're curious about where do you see this? I mean, Clarion Clipper Zone came up, the CCZ. Where does it make the most sense for you to set up operations? What was it, San Diego? Have you looked at setting something up in San Diego? The second part of that question is, I'm sure you guys have looked at stuff like that, but how far out? I mean, anticipating NOAA licenses coming through in 26, would you be ready to accept nodules in, say, 2027, 2028? Are you anticipating that? And the second question, so two parts on that first question. The second question, you briefly touched on, you mentioned, which was intriguing, doing this at sea on ships. Talk a little bit about that. That's very intriguing.
Yeah, I think there's a few different questions there. Are locations of processing? Yeah, and I may come back to you on to make sure I cover everything. We haven't looked at processing in San Diego. Of course, when you're setting up a business, you have to look at or setting up a processing operation. There are a bunch of factors, and that is everything from permitting to how much it costs to do business, to what the nearest port is, and that could be something in the U.S. Maybe Hawaii makes more sense. Maybe bringing it up to American Samoa makes sense. We haven't gone into and found a location for that. But because our technology is scalable, and instead of like a massive campus, I'll give you an example. RCA I mentioned earlier is a brownfield development. We're taking an old manufacturing plant that was used for something else and putting our columns in it. We require a light industrial area, and something like a small Amazon warehouse, we can do it in. For this though, I think there's a lot of factors that go into where we're going to place it, and we haven't settled on a location. I think there's a bunch of considerations to that. Going into your second part of putting it on ships, very early, but the point I wanted to make there is just how compact our technology is. We have We've seen systems. We have a system that would fit in a container. It's based on size and scale and what that looks like. And if that would be an opportunity to move the refining closer to where the material is being mined, that's definitely something we should look at. But I also want to highlight, while that's an opportunity, there hasn't been engineering done on that. We haven't developed a processing ship. But I do believe our technology enables that. And that is an opportunity in the future. But everything's always iterative. So what you're most likely going to see is a processing plant somewhere on shore. And then as that gets developed, how can we look at better solutions? And I'd go from there. And then was there a third question in there?
No, I think that was it. Just to be clear, what if you were to containerize something? You may not have an answer for this, but what would be the end product on something? Is it an alloy or is it a matte? What would be?
Question. Yeah. So for an alloy, that would be a pyrometallurgical process. So basically fire. When you think of pyrometallurgical, that's like a smelter. With us, we're a hydrometallurgical process. So our outputs are sulfates, chlorides, oxides, carbonates, hydroxides, stuff like that. So it wouldn't be a metal or an alloy. And then if you wanted to do the electrolyzing process on the end of that, that would go into a pure metal. For an alloy, you then need to do another process to get it into whatever alloy specifically. Is there the possibility that that could be done on ships in the future? I don't know, but maybe. But for our process, I think there is an option. A lot of considerations, though, because you are going to have waste. And what does that look like?
Great, thank you. I appreciate it.
Yeah, I mean, I think most of the battery customers, they would be looking for sulfates, so salts. And so that probably fits quite nicely, I think, with your flow sheet of what you could ultimately deliver. And as you talked about, you can get to the low impurity levels because that's also very, very critical for them. So I do see that we have some questions in the chat. So why don't we have a go at those? If other people have questions, please do raise your hand and we'll go to them as we have a bit of time. So Amos asks, I'll read it out. There's a view that it can take 10 to 20 years for new seabed mineral processing and refining plants to become operational in the United States. How would you react to that?
Thank you, Amos. Great question. For us, we can scale up in 9 months to a year. And again, 10 to 20 years, you're looking at legacy processing. You're looking at solvent extraction. You're looking at building a refinery. Building a refinery like a smelter is very, very expensive and requires a lot of permitting because we have less waste and less hazardous waste. And our CapEx is a fraction of the legacy technology and a smaller footprint. We can scale up in a year and a half, 2 years, depending on what the application is. So I would say, yeah, that's a very traditional view. And in many cases, they're right for that legacy technology. But that's an advantage that we like and that we take is we can just get to processing fast. And also when you're looking from a financial angle on it, if you're looking at permitting a refinery, you're looking at building a refinery and spending all this CapEx and going through the loans, you're trying to predict commodity prices years and years out and doing modeling. And then every time, let's say a country is impacting the prices or there's a flood of material on the market and the price drops, that changes your model, that changes how your investors look at it. With us, because we can move quickly, that financial model is completely different. We're looking at feedstock agreements and offtake agreements a year and a half, 2 years out when we're producing, instead of what can we provide you in 10 years and trying to adjust the geopolitical and macroeconomic forces at play. So we're just in a completely different model. Great
Yeah,
question.
yeah, and I would add, I mean, I think that's one of the huge advantages of startups and innovation is that we don't have to follow the old traditional way that, as people know, could take 10 to 20 years. It's innovation that allows you to do things faster and modular and quicker and better. The other thing that I would bring up is that if you look at the speed of the H-power plants that got built in Indonesia, this is the old style of technology, very bad for the environment, primarily built with Chinese tech and Chinese engineers, but they did them in like a few years. So if you don't care about the environment and you don't have huge barriers with permitting, even the legacy stuff can be built in just a couple of years, 2 or 3. But obviously, then you have huge environmental impacts that we are very aware of. For instance, like there's almost no fish left in around these islands in Indonesia because of all the pollution. So I think, you know, there are definitely ways to do it a lot quicker. I'm just looking if, Tony, you still have your hand raised, but I think we took your questions unless you have a follow-up you want to answer. No, maybe it's gone. Okay. So I had one additional question, Shane. We know that there are rare earth elements in the nodules, you know, neodymium, for instance. We've primarily focused on the primary metals, the nickel, the cobalt, the copper, the manganese. But what do you think of your tech being used to get the neodymium and some of the other rare earth elements that
Yeah, great question. And I also I'll address Kieran's question very quickly. Kieran, I'm not an engineer. I joke that I sometimes play one on TV, but there are some basic principles here. And for us to be able to provide you and you know this as an engineer, the energy consumption, the energy needs, the water consumption, the square foot for the land space, and a specific location on American Samoa, when we're just looking into it, it's not feasible for us to answer these questions today, and we'd also need to be under NDA. What I can say is, since our technology is scalable, it's going to vary based on what the initial production of impossible metals are, as well as kind of the long term, and it's going to scale over time. And same with sustainability. Sustainability is important to us, and that's why we try and minimize hazardous waste, or we do minimize hazardous waste and have a low environmental impact, especially compared to legacy technologies. And so these are all important questions that can't be answered today, but I do want you to know that we're considering those as well.
Thank you. Yeah, thank you.
No problem. Oliver, on the rare earth elements. So rare earth elements, they really aren't rare. They're rare in economic quantities in different places around the world. I'll give you an example. Lanthanum, one of the light rare earths, is actually 3 times more common in the Earth's crust than lead. When you're looking at NdPr on these modules, if you were going down and mining these nodules just for the NdPr, it probably wouldn't make that much sense. It's at pretty low concentration, and that wouldn't be a good business model. But when you are dealing with a nodule that is mostly nickel and copper and cobalt and manganese, and you can start pulling these off. Let's say they are 99% these other kind of base metals that we've talked about, and you are able to separate those and monetize those. That last 1% doesn't go away. It doesn't like disappear. You don't just throw it away. That's a concentration. And tailings and slag, those are all concentrations. And so what we can do is, even though the rare earths may have been a 0.5%, 0.25% of that overall nodule, when you look at it in that, what percentage of this last 1% are these rare earths, you have a substantially higher concentration. And then you look at it and say, oh, wow, this is economic to pull these rare earth elements out of that. And that's how we look at it, is what can we monetize off here and make economic sense, not just being technically feasible, but being economically feasible. And as we can monetize these other elements, every time you monetize one, if you're staying in kind of the same process, the others become concentrated. And with any processing, the higher concentration of that economic element makes the purification and the refining lower cost and makes that more economic in itself. And so we just would go through and then separate the rare earth elements as well, so we can help monetize the whole nodule instead of just one or two things. It's we eat the whole cow.
Yeah, I think that's great, and the strategic value to the US of getting these may also help, because we know China controls large quantities of rare earth elements, and the fact that they're in the nodule anyway. I completely agree. I think if you were trying to justify deep sea mining purely on the rare earths, it's probably going to be very difficult, wouldn't make sense. But if you're having them as a byproduct because you're already accessing the nickel, the cobalt, the copper, the manganese, and they're anyway, I think you more likely are going to process them as opposed to putting them into some waste tailing stream. So yeah, it makes a lot of sense. The other thing I would just comment on is, you've talked a lot about your scalability, and I think that's really important, especially for industries like ours, which can be capital intense, but it's scalable capital, and that's exactly how we've designed our collection system. It's modular around each robot, each Eureka robot, and so the more robots, the more capacity. And so we also have a very scalable approach compared to our competitors that need a complete ship and another support ship and another transport ship and another huge collector. They don't have that scalability, and so again, that's another reason why I think we can align our capital structure and our scaling structure together so that we both achieve success with small amounts of capital, and then we can grow quite quickly, which is another thing that I find particularly attractive. So I think we're at time. I want to thank everybody for participating, for the great questions. I want to thank Shane and ReElement for being a partner. Really happy we signed an MOU. I think they've got very exciting technology, and we're looking to progress and move forward, and ultimately be able to show everybody how together we can unlock what is the critical mineral problem for the US and the world. So thank you, Shane.
Thank you.
Thank you everybody for your time.
Thank you.